Hello everyone, my name is Jing. Today I can present our work UCNet uncertainty-inspired RGB-D Saliency detection via conditional variational autoencoders. This is co-work with Deng-Ping, Yuchao, Saeed, Fatemeh, Tong, and Nick. To start the talk, I will first introduce the concept of RGB-D Saliency detection. There mainly exist two sources of data, the RGB image as shown in the first row and the depth data as shown in the second row. The task of RGB-D Saliency detection aims to find the regions in the RGB-D image pair that attract human attention. Usually, RGB-D Saliency detection is defined as a category-free point estimation problem, where a deep neural network is trained to achieve mapping from input RGB-D image pair to the corresponding ground truth saliency map. Despite a lot of interesting work in this area, two main motivations inspire us to dig further into this task. The first one is the subjective attribute of saliency. To some extent, saliency can represent people's preference, and different people may lead to different attention map or saliency map, which indicates the subjective attribute of saliency. The second one is majority voting, which is widely used in generating the training data for saliency detection, where multiple annotators are asked to label one image, and the final ground truth saliency map is obtained through defining the majority regions as being silent. Both of the motivations indicate that point estimation may not be the ideal solution for saliency detection. We intend to model saliency prediction as distribution estimation via conditional variational autoencoders, where the subjective attribute can be modeled as a latent variable. The goal of CVE is to produce the structured outputs, where in our scenario, we want to generate diverse predictions representing people's preference. The objective function of CVE include two parts, the negative log likelihood as reconstruction loss and the KL loss, measuring our ignorance about distribution of the latent variable. Following the conventional CVE, we design a probabilistic RGB-D Saliency detection network, which takes RGB-D image pair as input and produces diverse saliency predictions with a random latent variable Z embedded in the network, representing the subjective attribute of saliency. 4 main modules are included in our network: LatentNet, Depth CorrectionNet, SaliencyNet, and PredictionNet. The LatentNet aims to obtain the latent variable Z, which takes the input image pair of the concatenation of input and output to produce a low-dimensional vector Z. The Depth CorrectionNet tries to improve depth quality and produce a refined depth. SaliencyNet is a typical saliency prediction network, which takes a refined RGB-D image pair as input and produces a deterministic saliency feature. The PredictionNet fills the stochastic feature of the LatentNet and determines the feature of the SaliencyNet to produce our final prediction. During testing, we can sample from the LatentNet to generate diverse predictions for each input RGB-D image pair and compute the majority of these predictions for performance evaluation. One drawback of conventional CVE is the posterior collapse problem, where the latent variable Z fails to contribute to the final prediction. To prevent this, we propose a new label generation technique by adopting the hide and seek method. We iteratively hide the foreground saliency map to generate multiple ground truth maps for each input image. Here we show the E mirror curve in the first row and F mirror curve in the second row to illustrate the effectiveness of the proposed solution. We also compare our method with multi-head and dropout-based structured output generation technique, and the experimental results show that our solution can lead to both high accuracy and diverse predictions. In this slide, we show 3 examples with diverse predictions. I really hope that one of them is consistent with your preference. To conclude, we argue that it's more natural and visible to treat saliency detection as a distribution estimation problem. And here, I share with you some tricks to train an effective CVE for our task. Firstly, we found that the dimension of Z really matters. Larger Z can improve diversity of prediction while decrease the network performance, while smaller Z may generate nearly consistent predictions. Secondly, the position to embed Z to the network may influence diversity of the prediction. And lastly, annealing the KL loss term can further produce better performance. Please find our code and results in the provided link. Thank you very much.